Hello, I'm Patrick Taylor, and in this video I'm going to be talking about an image format which I'm designing. I'll start off by saying why I'm designing it and giving a bit of history about already existing image formats, and then I'll dive straight into my ideas so far about what I'm going to do with it. So there's this thing we can do in sixth form called the EPQ, which is Extended Project Qualification. Basically it allows us to do some independent research outside of school and produce a thing at the end of the course. Quite often it's an essay. In my case it will be an artifact, as it's called. A thing, a program, an encoder and a decoder for my image format. And I'll start out with a bit of history of image formats in general. So image formats can be described as sort of two fairly separate camps, as the lossless image formats, which do not lose any information from what was originally taken by a camera or rendered by a program. And of course these tend to be bigger file sizes because you're storing everything precisely. And although they do try and incorporate some compression, it's hard to compress raw data like that. The other set are the lossy image formats. JPEG is probably the one you've heard of, and these, as you probably guessed, lose information. Not all the information is stored, but they don't lose enough for it to be that noticeable, if you're lucky, and if you've got your quality settings high enough. So my image format is a lossy format. It will lose information, but I'm hopefully going to design in a few features to sort of regain a little bit of that lost fidelity, but not the exact data that was there, but sort of in a pseudo way get it back. I programmed a proof of concept program over the summer to encode into a sort of, well, obviously not the fully fledged format, but my first idea of what it might be like, and that seemed to work okay. It was a very functional thing, it had bugs and everything, but the idea sort of seems to be there. So, what is my idea? Well, let's say we have an image, nice blue sky, someone covering up the top bit of the lens with their finger because they can't take photographs, and let's take a scan line across the top. So, looking at the colour intensity of every pixel along the top line of the image. And using this we can plot a graph. Well, we can plot three graphs actually. We can plot a graph for the red channel intensity, the blue channel and the green channel. And if you don't know, pictures can be represented by storing values of red, green and blue colour for each pixel, and combining these different values gives you different colours. So we can plot a graph. On the x-axis we have the x-axis really, corresponding to the x-axis of the image, and on the y-axis we have the colour intensity for each channel. And in many photos or images is my hypothesis really, there can be distinct sections of colour. So if we look at the example image, we've got a lot of blue in the blue channel, because the sky for most of the image, for most of that top line of the image, is just blue, it's sky. Or, well, it might be grey if you're in England, but let's say it's blue. And where the guy is covering up the image with his finger, we've got no blue, it's black, so the blue intensity drops off very steeply and just continues at naught. And we can express this as a series of simple functions, simple straight line graphs. Well, this was my first idea at any rate, to express each segment as a straight line graph. So you would store within the file the gradient, the y-intercept, the how far up each segment starts, and also the range of x values for which it's relevant. And the computer, when decoding, would work out the corresponding y values. This allows us, of course, to store not only straight lines, straight runs of data, which simple run length encoding might do, but it also allows us to store gradients. So if the sky morphed from a sort of dark blue up in the top right-hand corner to a sort of lighter blue in the top left-hand corner, we could store this as a nice gradient. I've realised since then I'm probably overcomplicating that, and I sort of went through which method would be best to store it. Could I store it as a Cartesian coordinate system? Should I store it in polar coordinates, or I store the angle and the x values? What I think is probably better is simply storing two coordinate points, the start and the end, x, y, and doing that for a series of points. I was also toying around with the idea of storing parameters for Bezier curves. I don't think this would be, firstly, easy to implement, and secondly, particularly useful. I don't really see there's much opportunity for images to have smooth gradients in them. I mean, there may be the occasional exception, but I think it would be rare. There is, of course, with the gradient method of storing, the potential for rounding errors. Let's say we're storing the gradient as a byte. This gives us, what, 0 to 255 values, 256 values. And, of course, the gradient isn't always going to be exact. There may be a decimal point in there somewhere, which of course will be rounded to the nearest whole number. And this can cause problems, not in just one gradient. We're losing enough information anyway for it not to matter if you're just in one gradient, but the cumulative effect across the image of all these errors could come to something fairly considerable. And I sort of toyed around with which value would be best to compromise on the gradient or the y-intercept, and from that I sort of realised that actually with each line segment, you could actually compensate for the error produced in the previous line segment by changing its gradient value slightly, so it ends up where it should be, and keep doing this along the image. That way, certainly the cumulative error would be minimised to almost nothing, really. Another interesting point is about colour spaces. Now, at the beginning, I simplified and said you could store images as a red channel, a green channel, and a blue channel. And, okay, I wasn't really simplifying, you can do that. That's a really widely used method of defining colour. But I have found an interesting method, and I've no idea what the convention is when saying this, so I'm just going to say it, YCRCB, or YCBCR, if you're getting the letters the correct way around. And this came, I believe, from old television sets, when the transition between black and white sets and colour sets was just taking place. The broadcasting companies wanted a way of transmitting all the data on one channel, one TV channel presumably. But how can you make a black and white set and a colour set compatible with the same feeds? You can't make the black and white set just look, for example, at the blue channel, or just the red channel, or just the green channel, and display that as a grayscale image, because the red channel, or the green, or the blue channel is not a true grayscale representation of the image. There will always be, well, quite considerable anomalies there. So they invented the YCBCR scale, and this stands for, if I can get this right, luminance, blue chrominance, and red chrominance. The luminance factor, the luminance channel, is the one that stores most of the information. This is a true grayscale image of the image you're trying to send. And if you just displayed that, you would get a lovely black and white image, just as if it were taken with a black and white camera. The red and blue chroma channels provide what small amount of colour is needed for the already provided shading in the luminance channel. The luminance channel has a far greater fidelity than the other two channels, so we can concentrate all our memory resources, or our storage resources, into storing this one channel, as opposed to having to split our resources equally between the red, green and blue channels in our other colour space. And we can sort of skimp a little bit on the other two channels, because they hardly require, because they require a huge amount less in terms of memory than the main channel. Now, one of the big problems with this is that we're quantizing hugely. So, if we have one of our segments, there's always going to be, in the original image, a little bit of noise associated with it. And that's kind of what makes a picture a picture. It's what makes it more real, it's what makes it good. And if we're just quantizing this into a single line, we're losing a huge amount of information there. Our image is going to look streaky and blocky and probably not that good. So what I'm thinking, and I'll have to do some experimenting with this, is to store some sort of noise value. So to store the intensity of noise associated with this segment. And on decoding, the decoder would get the standard Y values for this line, looking at your graph or however I'm storing it, and then using this noise intensity value, it would add a little bit of noise along there. And of course this would be a bit different each time, you wouldn't get the same image decoded each time, but it would hopefully create more of that realism that you're losing by quantizing the data into straight lines. Of course, we're taking scan lines down the image and storing each scan line, but equally, well, you could take a scan line or a scan column, I suppose, down the image. And for each separate image, one of these methods, along or down, is going to be better. So if my encoder is quick enough to do this, what I'm thinking is make it work out both possibilities and then choose the best one to encode in the file. And then there would be a bit, I suppose, at the beginning saying, hey, look, we're doing scan lines, or look, we're doing scanning columns. And the decoder would take that into account and decode your image, hopefully well. Now, my penultimate idea is probably the hardest. And it involves finding how our segments change as we go down the scan lines. Let's assume we're working in scan lines at the minute, because we always have been for this video. So, back to our blue sky. There's a lot of blue at the top of the image. So instead of storing, I don't know, however many tens of scan lines with the same or almost the same set of data, we actually store the first scan line, or the first segment for the blue sky, and we, somewhere in the file, perhaps at the end, or I'm not sure at the minute, I have to do some research on this, we store a value for how this segment changes as we go down the image. So we're effectively doing what we did with the image, but we're doing it with the scan line. We're modulating perhaps where the scan line is on the graph as it goes down the image. So on the first line there may be a lot of blue, full blue intensity. On the second line there's a little bit less, and on the third line there's a little bit less, and so on and so forth. And if we can find a nice expression for this, we could save a lot of space, I'm thinking, in our file. And my final idea is to do with anomalous spikes in our picture. Say we have a twig or something poking out into our image. So we've got a lot of blue for the sky, and then we've got a sudden spike down to nothing where our twig is, where it's black. And then the graph goes up and it goes to blue again for the rest of the image. We could spend a lot of data storing that spike. We'd have the start coordinate of the first segment, the end coordinate, and then we'd have the spike coordinate, and then we'd have the start coordinate of the final segment, and the end coordinate of the final segment. However, if we simply stored one blue segment, start and end, we can then store simply one coordinate, again, for the anomalous spike. So we effectively take away two of our data points, because we're storing a large segment for the whole top line of the image, and then one anomaly, one exception. So the decoder says, oh look, we've got blue all across the top of the image, but oh, right, at the end, yeah, we've got a spike down here, and it's nothing, just at this pixel, or a couple of pixels maybe. And I think that's another way to further reduce the image. These are the ideas I've had so far. I'm not saying this is going to work perfectly, really. I'm sure there'll be a lot of setbacks, and I hope I may have some more ideas about what to do. It'll require quite a lot of experimenting, research, finding out what's what, and hopefully I might have something reasonable by the end of it. I'm not saying it's going to rival JPEG or PNG, which have been in development for decades by top mathematicians, but yeah, I hope I might get something reasonable. Catch you next time.